Welcome to the Deep Dive. This is where we take fascinating sources you provide and, well, we dig into them. We pull out the most interesting bits, the surprising stuff.
Right, no dry lectures here. It's more of an adventure through the information.
And today we are going way back, late Jurassic period. We're looking at a really, really strange dinosaur, Ambopteryx.
Yeah, this one's a gem. We've got the actual scientific description paper as our source.
Okay.
So our mission, really, is to figure out what makes Ambopteryx so different. What does it tell us about how things like flight even evolve? It's got this combination of features that's, well, pretty unexpected.
Definitely sounds intriguing. So let's start with the basics. Ambopteryx. How do we say that? And what's the name mean?
It's Ambopteryx. And the name is actually quite descriptive.
Oh, yeah.
Yeah. Ambo is Latin for both, and
Yeah.
pteryx is ancient Greek for wing.
Ah, okay. Both wing.
Exactly, both wing. And that's a perfect little clue about its most standout feature. We'll get right into that.
Both wing. Love it. Okay, so where does this guy sit on the, the big tree of life?
Right. So big picture, domain Eukaryota, kingdom Animalia,
Yeah.
all the way down to Dinosauria, Saurischia, Theropoda.
Theropods. Okay. Like T-Rex and bird.
Exactly that group. And then more specifically, it's in the family Scansoriopterigidae, a pretty small group, but very interesting little theropods close to the bird line.
Scansoriopterigidae.
Got it.
And this both-wing creature, when and where did someone actually find it?
It was found pretty recently, actually, 2017, in Liaoning province in China.
Okay, China again. Lots of amazing fossils there.
Oh, absolutely. Near a place called Wubeiting Village. The rocks are from what's called the Yanli Albiota. Basically, they're the same age as the Haifunga Formation.
And that means?
That means late Jurassic, specifically the Oxfordian stage. So we're talking roughly maybe 160 million years ago.
Wow, 160 million years. That's
Yeah.
hard to wrap your head around. And was it just like a tooth or a bone fragment?
No, this is the amazing part. The main specimen, the holotype, it's cataloged as IVPP V24192. And it's stunningly well preserved. An articulated skeleton, so the bones are still connected and nearly complete. Even shows traces of soft tissue.
Soft tissue, you mean like the wings?
Exactly. Hints of the wing membranes. It's incredible. A direct window into that ancient world.
Unbelievable. So this fantastic snapshot was Ambopteryx huge or more manageable?
Oh, definitely on the smaller side. Based on this holotype, the estimate is about 32 centimeters long.
So like 13 inches.
It's about that. And weight-wise, maybe 306 grams. A bit over half a pound.
Tiny.
Pretty small. And the researchers think this individual was likely a subadult, or maybe fully grown. They can tell partly from how some bones, like in the tail, were fused.
Right, okay, small dinosaur. But the big story, the both wing thing, that's about the wings themselves, isn't it? This bizarre combination.
Precisely. That's the kicker. Ambopteryx had feathers, yes, but it also had bat-like membranous wings. Skin wings.
Feathers and skin wings, seriously.
Seriously. It's only the second dinosaur known to have this. The first one found was called Yi, also from China. Yeah, Yi. And our source paper calls Yi a sister taxon to Ambopteryx. Basically, its closest known relative, like an evolutionary cousin that shared this same weird wing setup.
Wow. So two related dinosaurs trying out this unique approach to getting airborne. What does the fossil actually show for the membrane part?
You can see it in the rock. It's preserved as this kind of continuous brownish layer. It's around the left hand, parts of the right arm, and even down near the abdomen. So it clearly shows this membrane stretching between the long fingers and the body.
Okay, I can picture that. And the feathers, where were they?
They found the densest feathers around the head, the neck, and the shoulders.
So a fluffy head and neck,
Yeah.
and then these leathery wings.
Kind of, yeah. It suggests, more typical feathered body covering in those areas, but then these very different wings. Not fully feathered, not fully membranous, a true hybrid.
What a strange mix, an evolutionary patchwork, like you said. Okay, let's dig into the anatomy. That super long third finger you mentioned, what was that about?
Right. The hyperelongate third finger. That's a real signature of this family, the Scansoriopterigids.
And they first thought it was 4.
Well, the initial idea was maybe for poking into holes to get grubs, like the modern eye does with its skinny finger.
Oh, the eye, that lemur thing with the creepy finger. Wild.
It's a cool idea, right?
Yeah.
Convergent evolution. But the current thinking for Ambopteryx has kind of shifted.
How so?
Based on this fossil, the evidence suggests that long finger was probably mainly for supporting that wing membrane, the patagium.
Ah, okay.
The researchers think the finger was likely embedded within the membrane tissue and probably didn't have much independent movement. So Maybe not so great for grub grabbing after all.
So less of a fork, more of a tent pole for the wing. That makes sense.
Hmm.
It's amazing how interpretations change. What about this other weird thing, the styloform element? Sounds technical.
It is pretty specific, yeah. It's this extra bone, described as elongate, a bit curved, extending off the end of the ulna.
The forearm bone.
One of them, yeah. The ulna. And its job, most likely, was to help support that wing membrane too. Like an extra strut.
Adding rigidity.
Exactly. Like a little spar holding the back edge of the skin wing taut. Nature's engineering.
So a long finger and an extra bone strut. It really committed to this membrane wing idea. What about the arms versus the legs? Were they weirdly proportioned?
They were. The forelimbs, the arms, were significantly longer than the hind limbs, about 1.3 times longer.
Okay. Long arms.
Yep. And within the arm, the ulna bone was actually shorter than the humerus, the upper arm bone. And the ulna was much wider, almost twice as wide as the radius, the other forearm bone.
Huh. Those aren't proportions for just, like, running around, are they?
Seemed like it. Really points towards some kind of aerial lifestyle, or at least something involving those forelimbs in a major way.
Built for the air, it seems. Now, the tail. You mentioned fused bones. The paper says it had a short tail ending in a pygostyle. That sounds like a bird thing.
It does, doesn't it? A pygostyle is that fused structure at the very end of the tail where tail feathers attach in modern birds.
Right.
Most dinosaurs in the theropod group that aren't birds had longer, flexible tails.
Right.
Ambopteryx, though, had this short tail, no obvious transition point, and fused vertebrae at the end, making this pygostyle.
Was that unique among non-bird theropods?
Not entirely unique, but definitely unusual. The paper mentions that some oviraptorosaurs and therizinosaurs also evolved a pygostyle independently.
Ah. So another example of evolution hitting on similar solutions in different groups.
Exactly. Like evolution was tinkering. It had this bird-like feature in its tail, even with these very unbird-like wings. A real mosaic.
Fascinating. Okay, let's switch gears slightly. What did Ambopteryx eat? Did the fossil give any clues?
It did, actually. In the abdominal area where the stomach would have been,
Yeah.
they found a few small gastroliths, stomach stones for grinding food.
Okay, some animals do that, like birds.
Right. But they also found what looked like large fragments of bone.
Bone in its stomach.
It seems like it. Likely the remains of its last meal.
Gastroliths and bone. What does that suggest for its diet?
Well, we didn't really know much about Scansoriopterygid diets before. But finding both those stones, which might help grind plants or insect exoskeletons, and bone fragments, well, it points towards an omnivorous diet.
Eating both plants and animals.
Potentially, yeah. Or at least insects and small vertebrates. Combined with its tooth shape, it really suggests it wasn't just eating one thing. This was actually a big deal, finding this dietary evidence.
So a more versatile little creature than maybe we assumed adds another layer. Okay, stepping back. The big picture. Why is Ambopteryx so important? What does it tell us about how flight evolved?
It's hugely important. Ambopteryx and its cousin Yi, they show us that the path to bird flight wasn't some straight, narrow road.
Right, not just feathers getting better and better.
Exactly. It looks like there was this period of experimentation, dinosaurs trying out different ways to get into the air. Membranous wings were clearly one of those experiments.
And the paper you mentioned, the 2019 Nature one.
Right, Wang and colleagues, that kind of says it all. A new Jurassic Scansoriopterygid and the loss of membranous wings in theropod dinosaurs.
The loss of membranous wings.
Yeah. It suggests that while feathered wings won out in the long run, leading to birds, these membrane wings were another evolutionary path that was explored, but ultimately didn't persist in that lineage.
So Ambopteryx is like a snapshot of one of evolution's alternative designs. A prototype that didn't make it to mass production.
That's a great way to put it. It reveals this hidden diversity in early flight attempts. We just didn't know about these membrane-winged dinosaurs until fairly recently.
And why didn't they persist? Any ideas?
That's the big question, isn't it? Maybe the membranous wings weren't as efficient for powered flight, or perhaps less maneuverable than feathered wings. Maybe they were more easily damaged. We don't know for sure.
Lots to think about. Okay, so let's quickly recap Ambopteryx. Late Jurassic China. Small dinosaur.
Check.
The both wing creature feathers and bat-like skin wings.
A key feature, absolutely.
Weird anatomy. Super long third finger, extra styloform bone strut, short tail with a bird-like pygostyle.
Yep, a whole collection of oddities.
And probably an omnivore, based on stomach contents.
Turns out, yeah, more versatile than we thought.
So it really underlines that evolution wasn't following a simple plan towards modern birds. It was trying different things out.
Precisely. The both-wing idea really drives home that diversity. Flight evolution was messy, experimental, full of these fascinating side branches.
It really makes you wonder, doesn't it, about those evolutionary pressures back then? Why did feathers win out? Looking at Ambopteryx and Yi, what advantages or disadvantages did their wings have? Why did that design fade away while the feathered path led to everything from eagles to hummingbirds? Something for you, the listener, to chew on. It definitely makes you want to keep digging into the fossil record, doesn't it?
Absolutely. There are always more surprises waiting.
Thanks for exploring the very weird world of Ambopteryx with me today.